Okay, so am I audible? Could anyone of you please reply like if I'm audible? So that will be very helpful. Okay then, if there is no one replying, I guess I will assume that I'm audible right now. And okay, we will wait for a few more minutes, then we can start because there are very few participants right now. So we'll wait for some more participants to join and then we can start. So we will wait for a few minutes. Okay. Okay then, I feel there are enough participants right now. We'll see if any other participant join, then that's fine. But for now, we can start. So welcome back to all of you. So like once again, if you may, please tell me if I'm clearly audible, so that there is no problem any further. You can just write in the chat box. That's completely fine. Yes, no. Okay. I guess then.
Audible, sir. Sir,
Oh.
audible, sir.
Okay, okay. Thank you so much. So that's fine. So okay. So then I guess we can start now. And so welcome back to the problem solving session or just simple interaction session for the NPTEL course of Fluid Mechanics and Application, conducted by Professor Vijay Gupta of IIT Delhi. So we are in week 2 of this course, and so in today's session we'll be discussing about fluid statics, mainly about fluid statics and its implications, and what are the forces that rise because of uh, in rise in static fluids. We won't go to in the forces that may arise because of motion of fluids, that to be considered in the fluid kinematics. But so for fluid statics, we only deal with the forces that arise because of a static fluid. It is a fluid in rest or uniform motion, as mentioned by Professor Gupta in his lectures. In uniform motion, in the sense that there won't be any velocity gradient between subsequent layers of the flow of the fluid flow. So it basically means that since there are no velocity gradient, so it means that there are no shear forces that could arise in the fluid flow, right? Because we have seen in the previous session that the shear forces given by, say that by for Newtonian fluid, it's given by mu the shear strain rate, or here we can write the shear strain rate as the velocity gradients, right? Del u by del y. So if u is uniform, then this gradient will go to 0, right? So there won't be any shear forces acting in the fluid. So that's why the only force that could act, even if the fluid is in uniform motion, the only force that could act is the normal force, and that is in this case is manifested in the form of pressure. Okay. So in today's session, we will discuss briefly about the pressure variations in liquid. That just remember that all these for static fluid. Okay. Okay. So pressure variations in static liquids, if I may say, and in atmosphere. Just briefly, And then measurement of atmospheric pressure, we'll briefly look into or skim through the various instruments that are being used to measure atmospheric pressure, because I guess Professor Gupta has very clearly and extensively discussed these topics in the video lectures. So I suggest all of you to visit the lectures for more clarification. We look into surface tension and its implications, and then we'll also look into manometry. I forgot to add, then for today's session we'll also look into forces on submerged bodies. And by forces I mainly imply to the pressure forces that act on submerged bodies in a static fluid. Okay, so this will be the agenda for today's session. So for a fluid at rest, it cannot, or uniform motion, it cannot apply a shear force on the surface. Like if we assume a small surface immersed in a fluid, and if the fluid is assumed to be at rest or a uniform motion, we cannot there cannot be any additional shear forces, just as discussed briefly sometime before, right? So there cannot be any additional shear forces. So the only possible force is a normal force, right? The normal force. Whatever may be the orientation of the surface, the only force that could act on the surface is a normal force, right? And this force is compressive and depends on the area of the surface. So compressive in the sense that we have discussed in the previous session, that the force is compressive because the force acts in a direction opposite to the direction of the area vector. So if this is the surface, say, and this is the area vector of the surface, then the normal force that acts because of the static fluid is in the direction parallel and opposite the direction of the area vector. So the force that acts in this case is compressive, right? Because it effectively compresses the surface of the body. So this force is compressive, and this compressive force that acts on the direction opposite to the direction of the area surface is termed as pressure in our case, right? And the units of pressure is given by Newton per meter square, because it's basically the force per unit area. So if you study or look into the domain of say solids, there's also similar term which has a similar a term that has behaves similarly and has the same unit, that is Newton per meter square, and that term is stress in the case of solids. But I just want to emphasize that the stress is indeed a reaction force instead of a compressive force, because stress arises in the solids because of a reaction to the additionally applied force on the solid, right? Because when we compress the solid, the reaction force that is being applied in direction opposite to the application of the applied force, that force is termed as stress. So just not to confuse it, because even if the units are same, the nature of forces or the implication that these type of forces have are different. So just to emphasize it on it, I mentioned it, so that's fine. Then we look into the Pascal's law. I guess it was discussed by Professor Gupta, and just a brief definition is that according to Pascal's law, the pressure at a point is same in all directions, or pressure at a point, pressure acting in a fluid is transmitted in equal magnitude in all the directions and the surface of the container, right? So there is a Pascal's law. We will again look into it and see some examples or applications where the Pascal's law turns out to be extremely useful in our day-to-day life applications. So I guess that's clear. Yes. So for stationary fluid, as I mentioned, the variation of pressure along the horizontal direction is given by dou p by dou x is 0. Right? I am just going through. You may feel that I am going very fast or not emphasizing on, trying to let you understand extensively with the help of schematic diagrams, because that's only being done because that has been extensively discussed in the video lectures. So repeating that once again, I guess, would be time consuming, because we have a lot of things to cover, with also with some additional examples in our agenda. So if I go on explaining each and every line in the lecture, so that would be very lengthy. So kindly forgive me not to be clearing all your doubts, because that would be very time consuming. So if you have any doubt, like, you can ask me, that's fine, but don't expect that I will go on to make you understand each and every topic thoroughly, because for that, I guess, it's better and wise to look into the video lectures, right? So I guess that's fine. So this term dou p by dou x equal to 0 basically comes out by balancing the forces in the, say there's a horizontal element, fluid element. So what we do is we basically just do a force balance in each of its side, and by Taylor's expansion we find out that so let me just draw it here. So this is P. So by Taylor's expansion, or Taylor's expansion of a function, say our function is P, and this is dou x, say. So the value of P at a point, at a distance of dx from say point A, so it's point B, then pressure at this point would be given by P plus okay. And by balancing these forces, we find out that in the case of static fluid, dou p by dou x turns out to be 0. So it basically means that there is no pressure gradient along the x direction in the case of static fluid. So if we assume our axis to be in this form, say x, y and z, so in the case of static fluid, there is no variation in the pressure along the x direction and the y direction, if you may say. Why? Because there is, other than the very weight of the fluid itself, there is no other force acting in the fluid, right? Because see, in the z direction we have a gravitational force that acts in the negative z direction, right? That's one force, that basically the body force that acts in the fluid element. But other than this, in the case of static fluid, there is no additional force that acts in the fluid element, right? Say in the x direction or the y direction. So the only force that acts is the body force, which acts in the z direction. So we will see that to balance this body force, we indeed have a pressure gradient along the z direction, right? So implying to that, we consider this again, we again consider this fluid element. Now we do the body balance along the z direction, because the force balance along the y direction will be similar to that of the x direction, right? So by doing force balance, we obtain an expression given by dou p by dou z is equal to minus rho g. So this expression is also known as a hydrostatic law. So it basically tells us that the pressure gradient that along the z direction is a constant given, which is equal to the negative of the product of the density and the acceleration due to gravity, assuming that the acceleration of gravity is taken to be a constant, right? So again, if we assume that p does not vary along x or y, we can convert this partial derivative into complete derivative, right? So that would give us complete derivative dp by dz is equal to minus rho g. Okay, so is it clear up to this point, like, or if you have any doubt? Okay, so assume that it is clear up to this point, because I also feel that it's quite simple up to this point, the hydrostatic law, and So you may just stop me like at any point that you may find that it's being a bit too fast or a bit confusing. So if you don't understand any concept that has been revised in this session, you can just stop me at that moment and I will try to clarify it. Okay. So given that there is no doubt, we can thank you. Given that there is no doubt, we can continue. So considering this expression, so this expression basically is a differential equation of first order, right? It's a first order differential equation of pressure. So solving that, basically we integrate pressure with respect to z. So given that and taking the initial condition that P is equal to P naught at z equal to 0, we get the equation P is equal to P naught plus rho gh, right? Where h where we substitute in this expression, let me write, right, y minus h, because h is taken in the negative z direction, right? That's why we substitute z is equal to minus h. Like if we want to measure pressure at a point, say A, which is at a depth of h, so taking z is equal to minus h, we can get that PA, in this case say PA is equal to P naught plus rho gs. So P naught can be a reference pressure or reference pressure, and in most of the cases, in the case of our day-to-day life applications, P naught is taken to be the atmospheric pressure in most of the cases. So it is quite safe to take P naught as atmospheric pressure, but it's very important that you mention it beforehand, and it's not extremely necessary, because in most of the cases I feel that it is quite understandable that the reference pressure, or here say P naught, is equal to atmospheric pressure, but still it will not be the same in all the cases, right? So it's very important that you look into the problem before just giving the value of the your reference pressure. So that's quite essential. But for most of the cases, I may feel that it's quite safe to take your reference pressure as the atmospheric pressure for most of the fluid flow problems, right? Because it is atmospheric pressure that is being taken as your reference pressure. So that's fine. And here, could anyone of you please tell me like what this symbol implies? Like,
this indicates free surface level.
Yes, exactly. Thank you. I'm sorry I couldn't see who replied, but whoever did, it's exactly absolutely correct. So thank you for mentioning. So this symbol, this inverted triangle with two dashed lines, with one the longer one above the shorter one, this symbol represents the free surface. See, as engineers, like though drawing is expressing our problems through the help of drawings is an important skill that any engineer should have, but we as engineers believe in technicality, and like if you just draw a surface and then solve the entire problem and just say that say you have drawn a surface, then you have drawn your diagram, and then just in case, like, because in the case of, say you are trying to represent a liquid in a container, and liquid in a container, and you mentioned that you mentioned two lines, one line showing the rim or the edge of the container within which the fluid is being kept, and the other line mentioning your free surface, right? And then you mention a coordinate system, say z, minus z, and then then you take the required depth that you need to take to do your required calculations, right? But if you just say in case have forgot to mention the specification of these two particular lines, the one who is evaluating your answers, say, like, may get confused, like which among these two lines refers to the free surface, right? The surface of the fluid, the free surface of the fluid, with respect to which you are taking your depths, right? So, as a technicality, it this symbol, the inverted triangle, has been used to denote the free surface, right? Like once you denote this, any examiner or any engineer who is evaluating your answers will be clear that this line is what indicates your free surface, right? It's not a big deal, but still, as engineers, some like it is good to focus on the specifics, right? So that's why I mentioned about it, and I hope you also have a practice of mentioning the free surface with the help of this symbol in all your problems, which makes your problem quite clear and understanding, and shows that you know what the specifics are and how clear your concepts are. So that's why. So that's fine. And now we look into some pressure measuring devices. In the case in this diagram, it shows a piezometer, which basically is a L-shaped pipe, I must say, an L-shaped pipe inserted in the center of duct or pipe through which a liquid flows, and helps us to measure the pressure at the center of the pipe by the help of the head, by the help of the rise of the liquid head in the vertical pipe, the vertical portion of the L-shaped pipe. Okay, this piezometer. So say this head is equal to H, right? Then the pressure at this point, say A, is given by P is equal to rho G H. Okay. How do we obtain this? It's basically obtained by the help of the hydrostatic law, right? That we looked just a while before. Dou P by dou Z is equal to minus rho G, right? Oh, sorry. Okay. So from this expression, basically we get this equation, and we already we again have this expression P naught plus rho G H. So this rho G H, you may see that I have ignored P naught in this case. So can any one of you please tell me what's it, given that P naught is P ATM, what's the difference between P1 and P2? Like, what does P1 and P2 represent? Like, how they are different? Okay. See, here P1 and P2 differ by a amount P naught, right? You can just write P1 is equal to P naught plus P2, right? Because where P2 is equal to rho G H. So here you can see that these devices, these piezometers, manometers, or any other pressure measuring devices, are mostly used to measure the gauge pressure, right? So gauge pressure means the pressure gauge pressure basically represents the difference between the absolute pressure and the atmospheric pressure, right? The reference pressure that we usually take. So in this case, P2 represents the gauge pressure, and P1 will denote the absolute pressure. Okay, so it clearly indicates that the piezometer that we used for measuring this for measuring pressure gives us the gauge pressure instead of the absolute pressure. So that's important to keep in mind, that in some questions they may mention that for us to use absolute pressure or gauge pressure, right? So it's very important that which pressure to take. Is it absolute pressure or gauge pressure? Because in some problems absolute pressure may be taken, and in some problems maybe gauge pressure may be taken. So if it's a problem include that comprises of piezometers, manometers, or other pressure measuring devices, say barometer also, those devices are used to measure the gauge pressure, not the absolute pressure. Okay, so I hope this is clear. Again, then this diagram represents the use of barometer to measure the atmospheric pressure. So I won't go through the entire explanation for this diagram because I guess it's being clearly explained in the video lectures, so that's fine. I'll just skip past it right now, because if you have any doubt, just go to our lectures, right? I just don't want to discuss it again, repeat it again, because I guess that would just be a waste of time. Okay, so again, atmospheric pressure variation with temperature. So this also I won't go discuss extensively. I just wrote the formula. So, and also for our case for our session and the problems that we are eventually going to discuss, we are not dealing with atmospheric pressure variation because of temperature. This you can just take it as a reference that helps you to know specifically that how temperature varies in different layers of atmosphere, right? So just for a reference, it is being mentioned here. So if at all we have to discuss pressure variation with temperature, and if we are going to deal with such kind of problems in the later future, I will discuss it extensively. But for right now, since we are not discussing such problems, you can just take these equations and the concept as a reference for your own reference or knowledge. So rather than going through extensively, because we are not dealing with such kind of problems right now. Okay, I hope that's fine. Okay, so again, as I told, we will again revisit the concept of Pascal's law. So because the application it has in our day-to-day life. Okay, so again I would reiterate the definition of Pascal's law. So Pascal's law states that the pressure applied to an enclosed fluid will be transmitted without a change in magnitude to every point of the fluid and the walls of the container. Okay, so say if this is your enclosed container, and these are the 2 points in the fluid. Okay, sorry, point 1, point 2. So the Pascal's law states that the pressure at these 2 points will be would be equal. Okay, because the fluid is enclosed in a container and the pressure is transmitted equal in all the directions. Okay, so that's why it gives us that P1 is equal to P2. Okay, and since P1 is equal to P2, we may write that in this diagram it basically shows that a force F1 is applied in this piston, say in this piston at point P1, which is used to raise a weight of F2 having giving a force F2. Say this is the weight that we are wants to lift, where the weight is being kept on a ram which has a pressure acting in it on its area, on its surface, which is equal to P2 in this case. Okay, so since P1 is equal to P2, we have F1 by A1 F1 by A1 is equal to F2 by A2. Okay, from Pascal's law. This is from Pascal's law. Okay, and then we can just write by just transferring the A2 to the numerator in the left hand side. We may write F2 is equal to F1 into A2 by A1. Okay, so it's a very simple mathematical expression, but has a very quite important implication in many applications, especially in the automobile industry or in industries where you are required to lift heavy weights. Okay, so it's clear that A2 is greater than A1, right? The diagram clearly shows that the area of the ram is much more greater than the area of piston that is being used to lift the weight, right? So A2 is greater than A1. So it tells us that by the help of this variation in the area of the ram and the piston, we can lift an equivalent load which is F1 times the ratio of the area of the ram and the piston, right? This multiplier. So it clearly shows that by applying a force F1 that can be like within a considered limits, like within a limit that can be within a limit that is possible to be applied by the help of some additional say some additional machines, right? Some machines may apply forces that has some certain limits, and we cannot go beyond that, but the weight that is being required to lift may be quite higher than the force that is being used to lift those weights, right? So how is that achieved? It is achieved by the application of Pascal's law, right? So you can clearly see that even though F1 may be small, like it may be quite less than F2, by the application of Pascal's law, it may be able to lift a weight F2 which may be quite larger than F1, right? So this is the application of Pascal's law, and it is being mostly seen in the automobile industries, where like we want to say lift some weights like to some higher elevation, right? To do that, we can use an external forces which may be quite less compared to the weight that we want to lift, and designs a similar equipment that satisfies all the required conditions of Pascal's law, and then used to lift a weight that is quite larger than the applied force. Okay, I hope I was clear. Okay, so again, Professor Gupta briefly discusses about forces in an accelerating container. So basically he touches upon the concept of rigid body motion. So I will also just briefly discuss this concept, the concept of rigid body motion. So here we may consider a fluid element that we used to derive the hydrostatic law and briefly sometime before. So we can consider a fluid element given by the red rectangle in this case, and the pressure that acts on each of its faces are P1 and P2, right, which are separated by a distance dx, which is basically the length of the fluid element. So this P1 and P2 would be governed by the height of the by the depth of these points from the free surface, right? And assuming that the container is accelerating, we may it accelerating in okay. Assuming that the container is accelerating, the free surface of the container will tilt, okay, and this tilt in the free surface of the liquid will give rise to different heights for point 1 and 2. Say this is point 1 and point 2. So this difference in the height of the free surface will give rise to difference in pressure, in the values of pressure at point P1 and P2, right? So applying the hydrostatic law again, given that assuming that the surface of the free surface of the liquid is inclined in the case of an accelerating container, P1 would be equal to rho g h1 and P2 would be equal to rho g h2, and taking h1 is equal to h and h2 is equal to h plus dh, okay. So I guess I have done a mistake in the drawing, so kindly forgive me. I guess the inclination would be in the reverse direction, in the opposite angle, so kindly forgive me. I have done a blunder's mistake, so I will draw the free surface again. Okay, so this is h1 and this is h2. Yes, now it makes sense. That's why I was thinking where I did a mistake, because the drawing wasn't making a sense for me. Okay, so we take h1 is equal to h and h2 is equal to h plus dh, because we can clearly see that h2 is greater than h1. So we take that h2 is say dh times more than the height h1. Okay, see like and our container is moving with an acceleration a in the positive x direction. Okay, so by applying Newton's second law, the net force acting on the fluid element would be is equal to mass the mass of the fluid element times the acceleration, right? So rho gh, we just balance the forces on, we balance the net force acting on the fluid element because of the pressure with equal to mass into acceleration, right, by Newton's second law. So it basically gives us rho gh minus rho gh plus dh is equal to rho dx into a, where rho is the density of the fluid element and dx is the length. And if we assume that the area of the fluid element in the dimension of the fluid element in the x, in the z and the y direction is 1 unity, then the area of the fluid element can be taken as 1, right? So the volume would be effectively given by dx into 1 into 1. So taking that into consideration, we can write the volume of the fluid element to be dx. So rho dx into A will give us a net force acting in the fluid element, right? So equating, solving this equation, we get the differential equation for the variation of height along the x as dh by dx is equal to minus A by g. Okay, so that is the concept of the net forces acting in a fluid element in the case of an accelerating, where when the fluid element is considered to be in a accelerating container. See, this kind of this kind of example can easily be seen in the case of a water tanker, like a truck carrying water in its container, like in a tanker, right? Water tankers, like if you have observed, say, the water tankers that bring about water in the cities. So these may be considered, these are the cases when we can see this kind of physics come into picture, right? A liquid having being filled up to certain height within the container. Say if the water tanker is being partially filled, so this would be the free surface of the water within the container, and if it is moving in with uniform velocity, or if it is stationary, the free surface of the water will remain horizontal, right? But once the container goes under acceleration, like there is a change in velocity, like it's going under acceleration, you will see that the free surface of the liquid would take certain inclined forms depending upon the direction of acceleration. So, like, just giving you an intuitive idea of how this tilt in a free surface occurs, right? So I hope it was clear. Just trying to give you an intuitive understanding, like in which case, in which scenarios such kind of tilt in the free surface could occur. So is the example clear, or okay? Thank you so much. Okay, then now we look into the concepts of manometry and surface tension again. So surface tension will be followed by manometry. So you can right now we just discuss about manometry in this case, like in this page. So that's fine. Okay, so the principle of manometry, like similar to piezometer, manometers are used to measure differences in the pressure between different pipes. Like say in the case of piezometer, it was only used to measure the pressure at the center of the pipe using an L-shaped pipe. So, and one of its end was open to the atmosphere, right? So it was open to the atmosphere, and one of its end was fitted to the center of the pipe, which gave us basically this head rise gave us value of the pressure at the center of the pipe, right? So this was the working principle of the piezometer. Manometer is exactly the same, but just its usability or the extent of its use increases in the case of manometer. Manometers can essentially be also used to measure difference in the pressure at two different pipes. Like say in this diagram, say in this diagram, okay. Say in this diagram, pipe A and pipe B can be can be taken as two separate pipes, right? And we want to measure the pressure difference between these two pipes, right? So to do that, we use the help of a different fluid having a different density, so that we can different density than the fluid that is being transported through these two pipes A and B. Different density, and also the fluid must be immiscible to the exiting fluids in the pipe, so that we can get a clear distinction in the interfaces of the two fluids, right? If the density is ρ1 and density of the fluid that is being used, the heavier or the lighter fluid given by that can be given by the density. Like if ρ1 is greater than ρ2, we can take the then if ρ1 is greater than ρ2, then ρ1 can be taken as a heavier fluid, so heavy fluid. And given that this fluid is immiscible to the fluid that is being transported in the pipes A and B, this distinction would help us to measure the pressure head difference between these two pipes A and B, right? So that is the working principle manometer, or this is how the usability of manometer is much more than in the case of a simple piezometer. Okay, so the way in which it is a very simple trick, by the way, in which pressure can be calculated by the help of manometer, right? So I will just tell you with the help of this example. Consider this example. Like this similar example was also taken by Professor Gupta in his lecture. So just to reiterate and so that the concept is clear. So if this blue fluid in the manometer denotes the manometric fluid that is being used to measure to obtain the pressure in the duct A. So what we do is we basically take, so if this is a diagram that is being given to you, so we basically take the lower end of the lower interface as our datum. Like there are two interfaces, right? At point 3 and at point 2. So since point 2 is lower, we take point 2 as our datum and then carry forward our calculations taking this as our reference, right? This datum point as our reference. Okay, so this is one trick. And again, like since the fluid at point 1 and point 2 is same, and given that these two points are at the same height, at the same horizontal level, we can write that P1 is equal to P2. Okay, so P1 is equal to P2, and P1 in this case would be given by P1 would be equal to PA, pressure at point A, plus pressure due to this liquid column. Okay, pressure due to this liquid column. So PA plus rho GH, H is given, so it's rho GH, right? And P2 is PATM, sorry. Why? Because this is open to the atmosphere, right? It's open to the atmosphere, so P2 is equal to PATM. Now you may tell that why you have not considered the pressure because of the height of this, because of the height of the fluid in this fluid that is being transported in duct A, right? So we can just assume that just for our case we can assume that, say this is rho f, rho f, we can just assume that rho f is much lower than rho, okay, the heavier fluid rho. So given that case, we can just neglect the pressure because of this liquid column and just take the pressure at point 1 is equal to PA, that is pressure at point A, plus rho GH, the pressure due to liquid column of the heavier fluid. Okay. So then given that we have the values of both P1 and P2, equate the two values and find that PA is equal to PATM minus rho GH. Okay, just equating the two values. Okay, so this is it's a very simple case. Like if it's a bit confusing, you may also consider to write rho f plus G, say this is H1, and that is H1. That's all. Then it will effectively become PA plus rho GH plus rho F GH1 is equal to PB, or in our case it is PATM. I'm sorry, P2 is equal to PATM. That's all. This will be your pressure balance, right? And we can use this expression to find the value of PA. That's all. So now again we look into another example. It's quite a bit more complicated than the first case, because in this case now we have an inverted manometer. So it's again quite similar, but let's just see what is a trick that is that we can use to measure the pressure in the case of this case, inverted manometer, which is a bit more complicated than the previous case, right? So again, here, like if we consider it to an inverted manometer, point 1 is lower than point 3, right? Like if you invert it, basically just invert this manometer, invert it, the interface at 1 is lower than interface at 3, right? See, it's not a hard and fast rule to take the datum like this. It's just a trick that makes the problem a bit simpler, but you can take this also as your datum and then carry forward your calculations. But since I find taking the datum at the lower surface, lower interface, so that's why I'm following this order, but it's not a hard and fast rule. Okay, so again, now given that I have taken my point, the interface at 1 as my datum line, so I can write P1 is equal to P2, right? Because both 1 and 2 has the same fluid and both 1 and 2 lie on the same horizontal level. Then we can write P1 is equal to P2. That's the first line. Then P1 would be equal to PA minus rho 2 G H1. Okay, see, here is the trick that I was discussing about. See, in this case, since we were okay, yes, since from datum line, okay, just I have to just excuse me for just a second. Okay, I'm sorry for the break. I'm sorry. So again, we can continue now. Okay. So in the first case, to get the pressure at point A, point 1, to get the pressure at point 1, we are going in the So we were going in a downward direction with respect to the point A. Okay, we are going downwards. Okay, so that's why if we go down, like if we go down our reference point to get the pressure, say if PA is, we are starting from PA and we are going downwards, then we add the value of the liquid column, right? We add the value of the pressure to the liquid column. That's why P1 was given as PA plus rho G H, because we are going downwards from our starting point. Now since we are going we are representing pressure since we are going from PA to 1 in the upward direction, that's why we have a minus rho to GH1 rather than plus rho to GH1. Okay, it's simple. Like if you are going upwards to from your starting point to get the pressure at the next point, that point where you want to obtain the pressure, if you are going upward, then you have to subtract the value of the pressure into the liquid column. And if you are going downwards, like in this case from A to 1, you are going, since we are going downwards, that's why you are adding the value of the pressure to your liquid column. So it gives P1 is equal to PA plus rho G H in this case. Okay, so if it's going up, then it's minus. If you're going down, then it's plus. Okay, so similarly now we can again write P3, where P3 would be equal to P2 plus rho, it is rho 1 G H. Again see, there's a plus, right? Why plus? Because from P2 we are going downwards to get P3. That's why we are adding the value of the pressure to the liquid column. Okay, similarly now if we take if you want to find the pressure at point B, then PB would be equal to P3 minus rho to GH. Okay, so this can be just taken in the case that if you again assume the datum at here, like if you consider datum at here, then from P3 you are going upwards to get the value of pressure at point B, right? So that's why PB would be equal to P3 minus rho to GH1. This is one technique, but we can again go take a longer path, that by having only this datum line we can try to obtain the pressure at point B, which has been done here. So I won't explain it extensively. It will give the similar results, it will give exactly the same results, but just like if I want to simplify it, I have taken for measuring the getting the value of pressure at point B, what we do is we take another datum at point 3, right, and then obtain the value of pressure at point B using the point pressure at point 3 as our reference. That's why PB is equal to P3 minus rho to GH. Why minus again? Because we are going upwards from our initial reference pressure, right, which is P3. So I hope this was clear. Could anybody please say yes or no, like is it clear? Because it's very simple and quite important. So I hope it was clear. Okay, so I'll assume that it was clear. So given that we have all our pressure values, we need to find PA minus PB, right? PA minus PB. See, this is an example from our Professor Gupta's lecture. So just reiterating it for clarification. You can always go back to lectures and clarify. Okay, so we just substitute the values of we just try to obtain the value of PA minus PB. So we can write this first expression as PA is equal to P1 minus, sorry, P1 plus rho 2 GH1. Then since we have both PA and PB, just do the subtraction. This is PA, this will be your PA, and this will be your PB, right? Then again you have P3 is equal to P2 minus rho 1 GH. We substitute that in this. Substitute P3 with this, so we get P2 minus rho 1 GH. Then just we arrange the values, we arrange the expression, because P1 minus P2 would give us 0. Why? Because we initially had that expression, right? P1 is equal to P2, because P1, point 1 and point 2 are on the same horizontal level and have the same fluid. That's why P1 will be equal to P2. So imposing that equation here, we get our final expression as PA minus PB would be equal to rho 2 G H1 plus H minus rho 1 GH. Okay, so I hope it was clear. Then we just reiterate some of the applications that had been mentioned in the video lecture. One was a reservoir manometer, or the speak manometer. One very popular example is the speak manometer. This is basically the blood pressure measuring device that is being used, the analog version of the blood pressure measuring device that is used in the hospitals and the clinics. Not a digital one, the analog one that has a mercury, which is used to denote your blood pressure, right? It will have a rectangular shape where there will be okay, I should draw it, I guess it's a bit difficult. So there will be a rectangular surface where you will have the mercury column with different scales denoting the value of your blood pressure. So once it is being pumped, like this is being pumped by the help of the doctors to measure your blood pressure. So I won't go into deeply in how the speak manometer works, but it's basically a type of reservoir manometer. So just look into it. Then again there's multi-tube manometer, which is, I guess in the lectures it was shown that it is being used to show the pressure variation along the surface of an airfoil, right? At different points along the surface of airfoil, a manometer or piezometer was inserted, which essentially gave us the value of the pressure at those different points, and showed us that how the pressure varied along the surface of the airfoil, right? There were different pressure points being made, and which were connected through manometers, right? And these manometers gave rise to different liquid heights, because the pressure was not uniform along the surface of the airfoil, it varied along the surface of the airfoil, and this variation was rightly captured by the help of these pressure taps on the surface of the airfoil, which were then connected to manometers to give us the reading of the pressure at those particular points. Okay. So see that the pressure variation along the surface of the airfoil is a continuous process, right? It's not discrete. It won't have a discrete value. Say at point 1, pressure at point 1 is very much different than pressure at point 2 or 3, like this. It's not like that. It's a continuous, because it's a continuous variation, and that's why it's called a pressure field, right? The concept of pressure field comes into picture. It varies continuously, right? There cannot be a distinct rise in the level of pressure like this, distinct rise or fall, the one that is being shown in the manometers. it's not a very accurate way of measuring the variation of. I'm not saying the values of the pressure at the shown by the manometers are wrong. No, it's not like that. But the trend of variation of pressure, that is the discrete values of pressure. Like I guess it was shown like, say these were distinct manometers. I guess it was shown like pressure, liquid head was like this, then it reduced gradually, then it again increased. See, this essentially tells us the discrete values of pressure at these distinct points, right? But it's not like that. We should not assume that the pressure varies distinctly. In principle, actually it varies in a continuous manner. So if we increase the number of manometers or pressure taps on the surface of the airfoil, say to a much higher value, then we can get a much more clearer trend of variation of pressure on the surface of the airfoil. Okay, so that's about it. And then again, Professor Gupta briefly discussed about inclined tube manometer and its fundamental application, like why it was designed in the first place. So it was basically designed just to have lower error in the measurement of delta H, right? Delta H, is basically this variation in the liquid heights in the manometers, right? This H can sometimes be very low, and the order of accuracy of these instruments would highly depend on this delta H. So if this delta H is very low, there is high chance of error in the measurements, right? And just to reduce that, or just to tackle that, an inclined tube manometer was designed, where instead of delta H, the measuring unit in our case would be the L, the length of the inclined liquid column, right? The inclined liquid column. This is basically an inclined liquid column. So this length is our fundamental requirement, right? The length of this inclined liquid column. So this would be higher than the value of delta H. So if it is theta, then delta H will basically be L sin theta. So since L would be larger than delta H, because sin theta is always lesser than equal to 1, that's why the error in measurement would be significantly be reduced, because instead of delta H, the parameter of our interest in this case is now L. So in some way the error in the measurements are reduced. Okay, that's why inclined tube manometer was designed in the first place. Okay, then there's Bourdon gauge. I again won't go discuss extensively about its working principle. I insist that you look into the video lectures, so it will be the best way to understand its working principle and the concepts. So okay, now we come into the concept of surface tension. So so to make you understand what actually surface tension is, let me tell you with the help of an example. Okay, so by definition, if I say, it's basically the additional forces the liquid that the liquid molecules have within them to overcome the forces that is being applied on it to break its integrity, right? So that's a simple definition, right? See, there are examples that have been shown where there was a liquid strider or an insect upon the surface, right? There was an insect shown upon the surface of the liquid, a very small lightweight insect. So if that's the insect, then it was shown that to have its legs spread around the liquid surface. So these were the these are the points at which the insect has impinged its legs upon on the liquid surface. So what's happening is that these insects the weight of the insect is causing the surface of the liquid to break apart, right? Because it basically is like, if we zoom it in, it will basically be a surface. It's being inclined. It will have its liquid molecules that are being attached with itself by the help of the cohesive forces between the liquid molecules. And the weight of the, say it is a zoomed in version of the leg of the insect, then the weight of the insect would cause these molecules to move apart, right? It will cause the surface of liquid to break and these molecules to move apart, right? But because of a force that is proportional to the length of contact of the body, say in this case the length of contact of the surface area or the lateral surface area of the legs of the insect, this force this force tries to adhere these liquid molecules with themselves instead of breaking apart, right? Like this force does not allow the liquid surface to break apart because of the addition of the external forces acting upon it, right? So this force that prevents the breaking of the liquid surface is known as liquid surface, because of the action of some outside external force that acts against the cohesive forces of these water molecules. So this force that prevents the breaking of these cohesive forces between the water molecules is known as surface tension, right? So there's another example that can help you to understand the concept. Like, see, you can assume a liquid in a container, a stationary liquid, say. So we may assume that there's a liquid bubble on the surface of the fluid, right? It's a very zoomed out version, right? There cannot be a liquid molecule that large, liquid droplet that large, but assume that it's a zoomed in version of the liquid. And because the fluids are different, like in the upper side is air and the lower side is water, so since the nature of the molecules of the air and water are different, so the molecules inside within the surface of the liquid will have high cohesive forces between them. Okay, this will have high cohesive forces between them. And with the air also there may be, since this is air and basically the densities are highly different and in fact the fluid is different, so this won't have any kind of cohesive forces. Like the upper surface of this liquid droplet won't have any cohesive forces acting between the liquid and between the water and air, right? There won't be any cohesive forces. So we can essentially see that there's a disbalance of forces between the upper and lower surface. So what should actually happen is that since this surface is being pulled in this direction, so what should happen is that this surface should eventually break apart, right? Since these surfaces are being pulled by the high cohesive forces of the water molecules, this liquid bubble should break apart or essentially open up, right? It should open up, right? Because there are no cohesive forces in this surface, and these cohesive forces are essentially pulling the boundary of this bubble towards it within the liquid. So this should break apart, right? But still this liquid bubble is able to keep its integrity, right? So that's why, because of the presence of this liquid molecule itself, we have a surface of water, right? So that's why this is not breaking apart, right? This molecule still exists and it keeps its shape. So this additional force, right, there must be an equal and opposite additional force that keeps the bubble from breaking apart. So this equal and opposite force that, so the, or in other words, by the virtue of this additional force by which the liquid bubble keeps its integrity on the surface even after having disbalance in the forces, this additional force that keeps this liquid bubble from breaking apart is known as the surface tension force. Okay. So, and this force, I hope I was clear, and this surface tension force is proportional to the length of contact of this liquid molecular bubble with the liquid surface. Okay. So in this case, the length of contact, if we assume this liquid bubble to be spherical, so length of contact would be the circumference of this circular area, right? The circular cross section. This would be length of contact. In this case, again, this should again be the circumference of, if we assume it to be cylindrical, the legs of the insect to be cylindrical, the length of contact would be the circumference of the legs of the insect, right? So if it's a safety pin, say if it's a small safety pin that floats on the surface of the liquid, the length of contact would be the perimeter of the pin, right? Perimeter of safety pin. Like if we essentially assume the pin to be rectangular, the perimeter of this pin, say, would be the length of contact of the pin with the liquid surface. Okay, that will essentially give us L. Since F is directly proportional to L, we can write F is equal to sigma L, where sigma is a constant of proportionality, and this sigma is what is termed as the surface tension. So since sigma will be equal to F by L, the units of surface tension is given by Newton per meter, force per unit length. Okay, so I see that we are running out of time very fast, so I will just skip past some of the concepts. So if you have any doubt, I suggest that you look into the video lectures, but still it has various applications. Okay, as mentioned by Professor Gupta, one of the very important application of surface tension is in the vascular bundles of our plants, right, the xylem and the phloems, where by the virtue of which the liquid from the water from the earth is being absorbed through by the help of this capillary rise, right? This capillary rise is also an implication of surface tension forces. So we'll briefly look into its formulas, not discuss it extensively, but it is by the virtue of capillary rise that the xylem and phloem, or the vascular bundles of the plants, are able to suck up water from the ground, right? So I guess that's it. And then again, there is a concept of excess pressure inside a liquid bubble. So it is given by 4 sigma by R. It is just done by measuring by balancing the pressure forces within the surface of the liquid bubble and the surface tension forces, right? Similarly, if it is a spherical droplet, instead of a liquid bubble, if it's a spherical droplet, the extra pressure or the excess pressure within the spherical droplet is given by 2 sigma by R, where sigma denotes the surface tension and R is the radius of the droplet, right? Essentially, the factor of 2 comes into picture because of the fact that instead of a single interface, now the bubble has 2 interfaces because the bubble is hollow, right? So it will have 2 interfaces, one within the bubble, the interface of air and liquid within the bubble, and the interface of air and liquid outside the bubble. So because of having these 2 interfaces and assuming that the thickness of this liquid layer is very small, we can essentially write the external excess pressure within the spherical bubble to be 2 times the excess pressure in a liquid bubble, in a spherical droplet instead of a bubble. So it will be 2 times the excess pressure of a spherical droplet. So yes, that's about it. Then again, one of the implications of surface tension can be seen in capillary rise. Like if we put a very thin capillary tube in a liquid, we see that a liquid column rises up by the virtue of the capillary forces that acts within the liquid. So that capillary rise in those cases is given by 2 sigma cos theta by rho gr. So I won't go extensively within this formula, so I suggest that you look into its derivation, where h denotes the capillary rise, the height of the liquid column that has risen up because of the capillary action. Sigma is the surface tension force. Theta is the angle of contact, the static angle of contact between the liquid surface and the container. And there can be 2 types of angle of contact, right? One is concave and convex, as shown in this diagram. So different types of fluid depicts or demonstrates different kinds of concavity, or in the case of in the case of the angle of contact. So different kinds of fluid will have different angle of contact. So in the case of water, it's usually an acute angle, so we will have a concave meniscus, and in the case of mercury, we have a obtuse angle of contact or a convex meniscus. Okay, so that's about it. So okay, so now we discuss the pressure forces on submerged bodies, right? It's a very important topic and quite extensive. Since we are limited in time, I guess I have to rush past a bit, but I will go through all the concepts and formulas thoroughly, and also some examples which will help you to consolidate your concepts. So if you have any doubt, you may stop me at that point. Okay. So I won't again go deep into derivations each and every point, because that has been covered in lectures. So right now I'll just go to the statements. Okay, so assume that a surface is in contact within a submerged completely in a liquid, and so the so the horizontal component of the, say if we are, say this is a container, I won't say the container itself will have some hydrostatic forces acting on its surface. So if this is a free surface of the liquid, and there is a plate, a rectangular plate being submerged in the liquid, so this this plate, or ideally I must say I can take the help of this diagram ideally. So assume that this is a curved surface that is being that holds height of liquid H, say, within it, right? So this is the liquid that is being contained within this curved confinement. Okay, so the presence of this liquid would exert some force on this curved container, right? That's quite obvious. So by intuition we can tell that the force would have the resultant force would have a direction of this form. So the container will also exert an equal and opposite force in the opposite direction, right? Where if we now decompose this force into its horizontal and vertical components, we may find that it can be decomposed into a vertical component that acts vertically upwards, and a horizontal component given by FH, right? So what actually this FH and FV denotes, right? So the horizontal component, or FH in this case, is the component of the pressure forces. The horizontal component of pressure forces is equal to the pressure at the centroid of the vertically projected area times the projected area. So in this case, if Fs denotes the horizontal component of this pressure force, so it would be equal to the centroid of the projected area. So if this is the curved surface area, so its projected area would essentially be a rectangle, right? So if we project this curved surface area, it will essentially be a rectangle, assuming that this has some certain width in the z direction, say x, y, z. If this container has some certain width, so the projected area of this curved surface area would be essentially be a rectangle, right? So this would be our A, and the centroid, if we assume this as a free surface, see the user technicality, how it verifies that it's a free surface. So if there's a free surface, then the centroid will basically be the half of the height of the rectangle, right? So it will basically be h by 2, if that is the centroid, right? Centroid. So basically it tells us that the horizontal component of the force would be rho g times h bar, which denotes the centroid of the projected area, and AV, which is the projected area. Okay, see, it's very important to know that AV is not the curved surface area, but instead the projected surface area of this curved surface. Okay, the projected surface area, that's very essential. Some people may mistake in that by taking the curved surface area or asking that it's quite difficult to find a surface, but it's actually very simple because it's the projected surface area and not the curved surface area itself. Okay, so I hope that's clear. And again, similar to the horizontal component, the vertical component of the pressure forces is equal to the weight of the liquid that can be supported on a surface up to the free surface of the liquid. Okay, so the vertical component of this force, the net force, will be equal to the weight of the liquid that is being contained within this container up to the free surface. So the weight of this volume of liquid, this highlighted red one, so this volume of liquid will be equal to Fv. Okay, so now given that these concepts are correct, so Fv will basically be equal to W. Okay, then given that these definitions and concepts, and hoping that you have attended the lectures properly, I'll go into some examples. So I won't directly go to the first example, it's quite difficult. So let's go to this example. So is my screen visible? Okay, so I assume that the screen is visible and you are looking into the example. So now for the remaining time, we will briefly discuss some of the examples. I suggest that you look into the examples and just stop me wherever you find there is some doubt. Okay, otherwise I will just skim through it, then it will be and then you will say you didn't understand anything. So that will be quite complicated. So let's consider this example. It basically denotes a rectangular plate submerged in a liquid. So this denotes the free surface, and so essentially our plate is being so this denotes the free surface. So essentially our plate is being submerged like this. So this is the projected area. So this is what the side view of the plate will be. So our plate is basically being kept like this. Okay, we have just twisted it and showed its side face. Okay, this face. Okay, so it is being submerged like this, and we are asked to find the center of pressure for this plate, like where the location of the center of pressure, right? See, the center of pressure holds its importance by the fact that see, we know that the buoyancy force, the buoyant force will act through the net buoyant force acting on a body could be assumed to act through the center of gravity of the object, right? Center of gravity of the object, which is being denoted by C. But in the case of hydrostatic forces, because the pressure variation is pressure varies linearly with the depth, the resultant of the hydrostatic force would not coincide with the center of gravity, because which ideally seems to happen, but because of this variation of the hydrostatic pressure, because the hydrostatic pressure is not uniform along the length of the object, and it shows a certain variation which basically increases along with depth. That's why the center of pressure which is basically the point through which the net pressure forces are assumed to act, is actually slightly lower than the center of gravity of the object. Okay, and that's why essentially P is in a comparatively deeper or lower than the center of gravity of the object. Okay, so there's a standard formula to find that out. I guess Professor Gupta mentioned it in the lecture. Say Yp would be given by Yc plus Ic by Ayc. Okay, where Yc denotes the depth of the centroid, Ic denotes the area moment of inertia about the axis passing through the center of gravity of the object. So that, because this can also be the axis by which the center of gravity of the object passes. This can also be an axis that passes the center of gravity of the object, but still it's now left up to the intuition of the students or the researchers who are working this kind of problems, which axis should be taken into consideration, right? So I will tell you the trick. See, given that this is the plate, right, we may eventually assume that this would be C and this would be P, right? So if we assume that this plate was hinged in some case, right, was hinged at bottom, because of the distance between these two center of forces, I must say, one denotes the center of gravity of the buoyancy force, and the one denotes the center of gravity of the pressure forces. So because of this distance between these two centers of forces, there is bound to have a net moment between these 2 points, right? The body will experience different, and if the direction of forces are different, then this submerged body is bound to experience some moment with respect to the hinged point, right? The point with respect to which the body has been hinged. So essentially this would cause the body to rotate in the, say, with respect to OO, the body would rotate along its horizontal axis, right? The body, since because of this distance between the two center of forces, the body is bound to rotate along its horizontal axis, that is given by this, right? And since essentially the rotation is bound to occur along its horizontal axis, so the area moment of inertia must be taken along that axis. So that's why we have considered the area moment of inertia given by passing through its horizontal axis, okay, which is being given by BH cube by 12. Okay, this is a very standard formula. I hope no need to derive it extensively and show how it's being obtained, but just to know if that is our dimension of our object, rectangular plate, how to find the area moment of inertia along its horizontal and vertical axis. Okay. So given that we know that, so IC is the area moment of inertia. So this is the formula that was being derived to find the center of pressure of any object being submerged in liquid. Okay. So given that configuration, the net force, the net horizontal force that acts on the plate is given by rho g AHC. Okay, where HC denotes the center of gravity of the object from the free surface. Right. So rho g is rho g. It is not because we are trying to obtain in terms of the system parameters itself, not giving specific values to these parameters. So rho g remains the same. A is given by area of the plate is given by BH, breadth, the breadth and the height of the plate, and HC, the center of gravity, is given by A plus HC. Why A? Because we need to consider the center of gravity from the free surface. Okay. So it is being kept at a certain depth A, so we need to take into consideration A plus h by 2, right, which gives the location of the center of gravity. So F is given by rho g bh A plus h by 2. Okay. Then to find a center of pressure, again we use this formula. So YC would be equal to A plus h by 2 as discussed here. IC would be BHQ plus 12 because of the that is the area moment of inertia with respect to the horizontal axis, and AYC, A would be the area of the surface that is being immersed, so that will be BH plus again YC would be equal to A plus h by 2. So that basically is the expression. So now if we have some numerical values to these values of B, H, G, rho and A, we can substitute those numerical values and essentially find the value of center of pressure YP. Okay. So okay, then we look into this problem. I hope I'm able to explain it to you properly. Okay. So consider this diagram. Okay. A gate hinged at B will open automatically when the water level at H, this water level becomes high enough. Determine the lowest value of H for which the gate will open. Okay. So I will hide the solution right now. So am I audible? Like there are only two students right now, Shivendra and Stephen, if I am pronouncing the name correctly. So if both of you are able to follow what I am telling, so have you understood the question? Please.
Yes, sir.
Okay. Then could you tell me at what instant the gate will open? Right. See, we know that the pressure forces act along the center of pressure, right? So let me zoom it in and erase these values. Not erase actually. Say these are 1, 2, 3 and 4. So these are, for example, these are the 4 points of application of the pressure force. So 1, 2, 3, 4 basically denotes the position of the center of pressure of this for this plate. Okay, this plate. So could both of you please tell me, or anyone from both of you please tell me that at what point at point 1, so if the pressure center of pressure is at point 1, will the gate so if the center pressure is at point 4, say, so will the gate open? So it will basically mean that there is a force that acts along this direction, and this is a stopper, so it will stop the gate from rotating. So if the center of pressure is at point 4, will the gate open? Yes or no?
No, sir.
No, right? So again, now if the center of pressure is at point 1, will the gate open in that case?
Yeah, in this case, gate will be open.
Yes. Why? Because this will essentially give a counterclockwise rotation to the plate which is being hinged at point B. So the gate will essentially rotate in the counterclockwise direction, making causing the gate to open, right? Because there is no stopper here, so the gate will essentially open, right? So similar to that argument, we can say that at point 3 also the gate won't open, because it's quite close to hinge, but still it's below the hinge, right? It's below the hinge, so gate won't open. So essentially, according to the need of our question, the point of application should be at point 2, so that the gate just opens, right? The moment the center of pressure crosses the center of the hinge, right, crosses the hinge, the gate will open, right? So keeping that argument, we follow the same formula, that our Yp, the center of pressure, is given by Yc plus Ic plus Ic by Ac, right? All the terms I have explained, what denotes what. Then Yc would be H plus 0.5, right? Why 0.5? Because the length of plate is 100 centimeter, basically 1 meter. So I take the center of gravity of this plate would be at H plus 0.5, right? 0.5. Then Ic would be BH cube by 12. So B is again in this case 1, and H is also 1. I'm sorry, I forgot to mention the dimensions. So it's a square gate. So assuming that the depth is 1 again, so I will just mention it. It is best. Assuming the depth is 1 meter, then it is basically BH cube by 12. So BH are equal, so 1 divided by 4 by 12. Then area is again 1 square. Then Yc is 0.5 plus H, right? So it basically tells us that for the gate to open, this center of pressure must be less than or equal to H plus 0.6, right? H plus 0.6, this height. The center of pressure must lie above this point so that the gate will open. Is that clear? Okay, I'll assume that that's clear, because it's quite simple but quite conceptual. So that, and it takes into consideration all the concepts that you have learned till now about the hydrostatic forces acting on immersed bodies. So it's a very good example actually. That's why I'm emphasizing it upon it that much. So this center of pressure should be less than or equal to H plus 0.6. Okay. Now by solving this equation, we just solve this equation to get that the value of H should be greater than or equal to 0.333 meter. Okay. So this was about it for this example. So we again look into another example. I guess because of our time restriction, I guess this should be our final example for today. So what we are asked is that find the horizontal and vertical components of the hydrostatic forces on the cylinders, where the length of the cylinder is being given by 3 meter and diameter is 2 meter, as shown in figures A and B. Okay. So the figure A shows that a cylindrical surface, so it will essentially be a cylindrical surface that is being kept between two different liquid levels. Okay. So this is the free surface at the left and this is the free surface at the right. So to simplify the problem, what we do is we decompose the cylinder into 4 different quadrants, 1, 2, 3, 4. So here, as mentioned here, in the first quadrant, the net force acting on the first quadrant would be 0. Why? Because this quadrant is not at all in contact with the liquid, right? So there is no hydrostatic forces that acts on the quadrant 1. So the both FV and FH, this is F vertical and the F horizontal, would be 0. Okay. For the second and the third quadrant, I would like to include both of them together, like just including this entire semicircle. So for these two quadrants, FH would be equal to the weight of the liquid that is being supported within this container, right? So for that case, the volume of the liquid, this is again the case of liquids, again the case of an apparent case where even if it is similar to the case where when the liquid surface is in contact with liquid but does not enclose the liquid, okay, does not enclose the liquid. Similar to that case, quadrant 2 and quadrant 3 shows that even if it does not enclose the liquid within it, because there is no liquid within this container, it has a liquid element, it is in contact with the liquid in its outer surface, right? So in this case, as discussed by Professor Gupta in the lectures, what we assume is that the liquid is being we assume that the weight of the liquid within this container up to the free surface. So so the net force that would act in this case would be a vertically upward force that would have been caused because of the reaction force of a liquid enclosed within this container, okay, this semicircle shaped container. Okay, see, in this case there is no liquid within the container, okay, there is no liquid within the container. Till now we have discussed the case where the liquid contains the container had the liquid confined within it and those directly, like similar to this case, it was confined within the container and the weight of the liquid was directly given by the liquid confined within the container. But since the force was then acting vertically downwards, okay, because the weight would essentially act vertically downwards. But in this case, since no liquid is contained within the container, the net force that acts would be actually a reaction force that would have been there if there was a liquid confined within this highlighted container, okay, this quadrant 2 and quadrant 3. So FH would be equal to rho GV, okay. So V is the volume of the liquid, the apparent volume of the liquid within the quadrants 2 and 3. So it is given by 1 by 2, this is basically the half of the volume of the cylinder, pi by 4 d square into L, right? So this calculation will give us Fs equal to 46.23 kilonewton acting vertically upwards, okay, not downwards, vertically upwards. Why? Because there is no liquid, in actual there is no liquid contained within this container. That's why there is a reaction force that acts vertically upwards. If there is a liquid within the container, this Fh would have actually acted downwards, right? So Fh is equal to 46.23 kilonewton. Again, similar to that, since there is no liquid here, we take the apparent apparent force that the liquid would have exerted if the liquid was contained within this confinement. Okay, so the vertical, I confused with the terminologies. This would be the vertical force, actually, and this would be the horizontal force. Forgive me for the silly mistake. So the horizontal force in this case would be again rho g h into a, where a is the projected area. So in this case also the projected area would be this rectangular surface, right? This rectangular surface. So it will basically be given by rho g h a. So rho is 1000, g is 9.81, h is 2, because this is the centroid with respect to the free surface. So it will give I'm sorry, this should be 1. Centroid is 1 and area is 2 into 3. 2 is the diameter of the cylinder and h is the length of the cylinder. So a projected rectangular area. Okay. So this gives us Fh is equal to 56.86 kN acting in the rightward direction, right? Because if there would have been a fluid within this container, the force that would have acted in this surface would have been in the left direction, right? Okay. Again, for the fourth quadrant now, the free surface of liquid is up to this level. So again, this surface does not contain any liquid within it. So it will only be the apparent weight of for the vertical forces. It will be the apparent weight of the liquid that would have been contained in this fourth quadrant. And now, why we are not considering the first quadrant also? It's because it's only the liquid, the weight of liquid content up to the free surface that is being considered, right? So since the free surface is up to here, we consider the weight of liquid up to the free surface. So F vertical would be equal to the weight of the liquid, the apparent weight of the liquid that would have been contained within this fourth quadrant. Okay. So again I have made a mistake. So Fv is equal to rho g v, right? So Fv equal to rho g v, then it gives again, so we just substitute the values. So 1000 in 9.81, 1/4 of the volume of the cylinder. So this gives us a net force acting vertically upwards. Okay. Similar to that, the F horizontal will be given by rho g ah, where rho is 1000, g is 9.81, a is 1 into 3, because this is the area. So it's 1 into 3 into 0.5, because that is the position of the centroid, right? So it will essentially give us net force acting in the leftward direction. Okay. And then just to get the net forces along the horizontal and the vertical direction, we add the surface, add or do the vector addition of these forces and then obtain the net forces. Okay, so I guess because of our time limit, I have to stop here. In the next week's session, we will discuss briefly about the stability of submerged bodies, because that part we couldn't cover because of our time limit. So we'll cover that in the next session briefly. Just look into the formulas and take some examples, and then continue with the contents of week 3. So again, thank you for attending today's session. I insist that you attend the Sunday session as well to get more clarification, because there might have been certain moments where you might not have been clarified, might not have been that clarified by this session. So I insist that you attend the Sunday session as well. And again, I insist that you also thoroughly attend Professor Gupta's lectures, because again I emphasize that those are the best sources for us to learn and understand the concepts in the best way possible. So thank you again. So if you don't have any doubt, I'll end the session here. So thank you.
Thank you, sir.
Thank you so much.